Hey everybody, this is Noah with Learn Meta-Analysis, and today we're going to do a tutorial on how to do a 3-level meta-analysis using simple meta-analysis software, which is just a point-and-click software, and we are going to go through the entire process from start to finish, including calculating our effect sizes. So we're going to use the same dataset that we have used many times. This one, as you can see, is just called Demo 3-level on my computer right now. So you can see here we have our experimental group mean, standard deviation, and sample size. And we also have a control group mean, control group standard deviation, and control group sample size. So this is the data set we're going to be using. So let's go ahead and get started. So from the simple meta-analysis intro screen, we're first going to go to the effect size calculator and then standardized mean difference. So you can see we have some instructions here. It has to be in CSV format, and we have to have these columns labeled these specific things. I already actually did this. So we're going to go ahead and upload that data set. We're just going to scroll down here, click on Browse. It opened up on my other window, so I'm just going to go ahead and grab that file real quickly, and you can see it read it in. So I'm going to hit Calculate, and it's going to compute this for us. So you can see it looks a little bit weird here. It's just because of how much text and everything there is. But if we scroll all the way down, you can see we have this YI and VI columns that were added that were not there before. And these are our effect size, YI, and the effect size variance, the VI. So we're going to go ahead and save this file because we are going to need this to move forward in the rest of our analyses. So I'm going to go ahead and I'm going to click Download Data. And I'm actually just going to leave it in my downloads folder because that's perfectly fine with me for now. Typically, if I were doing this for real, I would save it, somewhere much more secure than my downloads folder, and I'd also name it something else. But for our purposes today, that's going to be just fine. So next thing I'm going to do, I'm going to go over here to 3-level meta-analysis, and we're going to first check out data formatting. Now, there's already instructions here. There's an example table, blah, blah, blah. I already know, because I set up the data set and I built the software, I know what needs to be here. But there's a couple things that I want to point out that are actually really important. The first one is this ES_number. This has to be included in your data set. You need to have a column labeled study, and you also need the YI and the VI. That is the absolute minimum that you need to be able to run a 3-level meta-analysis. So you can see a sample data file down here, and you can see we have effect size number, we have study, and actually I'm realizing I found a little error in this example data set. I do not have my YI and VI in this data set, and that's because this one was the one that we just used before I actually calculated that. So I'll have to fix that at some point. Long story short, let's go ahead and start running the analysis. Okay, so first thing we're going to do is we're going to click on this step 1, run the analysis button, and we are going to go here and choose our data set to upload. So I'm just going to click on that. Again, it opened up on my other window, so I'm just going to grab my data set quick. You can see my data3.csv, and I'm going to click run. And boom, we're done. Right, so very, very simple here. Let's take a look at what these results mean. So first and foremost, we can see our overall effect size is 0.286, so we'll say 0.29. It is statistically significant. You can tell that by looking at our p-value here. It is less than 0.05. We also see our degrees of freedom, our t-value, and our confidence interval. But the next thing that we're probably going to want to look at is our test for heterogeneity. And you can see up here that this is significant. Okay, so we know there could be some we know there is some significant heterogeneity in our sample. And then up here, we can see our tau squared values. The first one is the sigma 2.1. This is our between studies. And then sigma 2.2 is within studies. Okay, and so what we are looking for here is essentially this estimate, and so this can be interpreted in the same effect size as the effect size that we are using in our analysis. So in our case, it's standardized mean difference. So in this case, we can see that we have more heterogeneity within studies than we do between studies. So one other thing that I'm going to point out, I'm only going to point out probably on this page, is that for every analysis that we do here, we're going to get the R script so that we can replicate this using the actual code in R. So we have that code down here, and then you'll see that we also have some methods notes. So we're doing a 3-level analysis using REML, and we used, we nested the effect sizes within studies. We also used a t distribution rather than a z distribution. All of these types of things are actually very important for when you go to report your meta-analysis. Like, you would want to make sure you specify that you used REML, you want to make sure how you set up your 3-level structure, and you want to make sure that you note that you used a t rather than a z distribution. And I include a link here so you can read more about that if you're interested from the metaphor documentation. So next thing that we'd want to do, at least that I like to do, is I like to download these results. So I just click this button and it's going to throw it into your downloads folder for you. So let's go check out the variance that we have here, okay? So I'm just gonna go to step 2, explain the variance, and I'm going to once again upload my data set, which you can see, you saw it pop up for a half second there. It opened up on my other monitor, so I just choose that same data set and I hit calculate. All right, so let's see what we have here. You can see we have within clusters and between clusters. Now, something that usually, I don't know, I don't want to say it always confuses me. I think now I'm finally at the point where it doesn't confuse me literally every single time that I see it. But when we were looking at our overall results, so when we look at our overall results here, you can see we have our between studies first and then within studies second. But then when we go to explain the variance, we have the opposite. We have within studies first, and then we have between studies. So be really careful you don't get confused by that. That was something that took me a long time to kind of like get straight in my brain. I don't know why. I think I just like things being in order. But anyway, let's go ahead and start interpreting this. So we have our I-squared column here. And what we can see is that we have 99.18% of the variance coming from within clusters and 0% coming from between the clusters. And then our total I-squared is at 99.18. So what I like to do is I just like to double check that this aligns with my tau squared. And fun fact, it always does. But I still like to check it just because it helps in my brain make sure I'm understanding things right. So I have my within clusters here, and it's 99% of the variance coming from that. And so what I like to do is go back to run analysis, and then I look again at my tau squared. And you can see that my tau squared was higher for the within clusters, which is the 2.2, than the between clusters. And we would have expected it to be 0 because our tau squared is 0. So long story short, I just like to make sure that these align, and they should with the way that the analyses are written in here. So what does this mean? This means that the variance in our sample is coming from within studies rather than between studies. Okay, this is good for us to know. And I'll also just point out that we do have our R script here if you need to replicate your analysis. And I always recommend that you report your R script when you write up the actual publication on the paper so other people can replicate your work. All right, so now we're going to go ahead and check for outliers and influence, and we're going to do this in a couple different ways. First, we're going to calculate outliers using Van Lissa's method, and this is very conservative. We'll talk a little bit more about that in a few minutes. And then we're going to check for influence using Cook's distance, DF betas, and hat values. So again, we're just going to upload that same data set, and we're going to hit run. Now, as you can see, this takes a minute to load. There's a warning about that. There's a progress bar down here, but it's already done. So you can see we have our outliers. Our outliers show up as this bluish green color. Sorry for those who may be colorblind, but we have we have 5 potential outliers here. We have one all the way over here, and then we have a couple more on the right side of 0. Now, the definition of outlier that we used is that the confidence interval does not at all overlap with the overall meta-analytic effect size confidence interval. Okay, so this is a pretty conservative indicator, but it gives us a good benchmark to go off of. So what do we do when we have outliers like this, when we see there's potential outliers? Like, the first thing I like to do is go back to my data set and make sure that I don't have any typos. And to be honest, a lot of times this is what happens, especially if you have an effect size that's like way off to the side. You just made a typo somewhere, or sometimes you just put a decimal in the wrong spot, that kind of thing. And if that's the case, I just fix it, and then I go back and I rerun the analyses that we already did, which thankfully takes like 4 seconds because it's all point and click, right? So we can go back and we can fix that error. The next thing I do is, let's say that I didn't have any typos, all the data looks good, I check it against the primary studies, everything's looking great. Then the next thing that I would do is look at the primary study that is an outlier. What I'm checking for when I look at this is to see if there's anything notably different than the rest of the studies in my sample. And the reason is because outliers can significantly move, or they can potentially have significant influence on your overall analysis. We're going to talk more about influence here in a minute. But it's good to know, is this study something that should actually be in your analysis, or is it really quite different than everything else that's there and it's going to skew your results? So those are things that you need to decide. But before you make that decision, let's check out the influence statistics, okay? So as we scroll down here, the first thing, okay, I forgot to mention, sorry. On the outlier results, you can download this plot, and that's just going to throw it in your downloads folder like usual. And then we get to the influence results, we can download this as well. But as you can see, we have each each comparison from each study here, and then we have columns marked outlier, Cook's flag, DF beta's flag, and hat flag. And if these are marked true, that means there is significant influence, or it is significant outlier if it is in the outlier column. So scrolling through here quickly, we can see we have a number that are outliers, right? And we can see we only have one that looks like it has some significant influence to it as well. And this is this study right here that's labeled Kim 2009 Experiment 2, and it has a strong negative effect size of -2.82. Now, I know from looking at this data set in the past that this study is well conducted. There's nothing notably different than the rest of the studies in my analysis. So even though this is significantly influential, I am going to leave this in there. And the reason is because I believe it is a valid study, and it is important for our overall analysis that this study be included. Now, one thing I do note is that I do make note of these in my papers when I go to publish. So I say how many outliers I have. And in this case, I would say this study was significantly influential by 2 of the 3 metrics that we used here. Okay, last but not least, well, I guess there's more than one last but not least. So second to last but not least, I want to mention the methods notes again that are here. They basically give us very generic overview of what we did. Again, we used REML, same as our overall analysis, 3-level structures the same, and we use the t-distribution again. Okay, then I want to point out that there is the R script here for rerunning all these analyses if you need it. So let's move on, and let's run a categorical moderator analysis. So again, we're just going to upload our data file, and then we are going to choose our column. Now, I haven't looked at this data set in a very long time, but I know my own brain, and when I have something _C, that means it's a categorical variable. So I'm going to go ahead and I'm going to click Control_C, and I'm going to run the moderator analysis. Now, I want to point out a few things here, okay? Moderator analyses in R, if you are doing categorical variables, there's 2 different tests of moderators, okay? When you look at the actual R results, and they tell us different things. So the first thing that we typically want to know with the categorical moderator is, are there significant differences between groups of them or between levels, okay? So in this case, the levels would be no intervention, software program, traditional training, or video. To get that test of moderators, we want to be looking at the model that includes the intercept. Okay, and if you look, you can see you can download those full results straight from R right here. Now, to get a table like this, you actually need to rerun the model without the intercept. And because when you have an intercept in here, one of these levels gets assigned as the intercept, and so it's not going to appear this way. You get the same numbers if you do some math, but it's not the way that, like in my field, we would typically report it this way, not the way with the moderator, not the way with the intercept. So we end up running this twice. What we do is we run it first with the intercept model. That gives us our test of moderators, which appears right here. And there's notes about this, by the way, in the methods notes and basic interpretation tips on this page. But we'd first run the intercept model to get our test of moderators. Here we can see it is not statistically significant because our p-value is 0.32. Next, I would run it without the intercept so that I can generate this table. And as you can see, I already did this for you. And if you click download these formatted results, this is going to give it to you as a CSV file with all of this information. And so why would you want to do this? Well, number one, personally, I find getting tables out of R to be really tedious, and I do not like doing it. And so the primary reason I built this was because I was sick and tired of trying to get my data out of R, and this was one way that I could do it and never have to mess around again with trying to get my data out of R in the format that I want. So here you can see N experimental. This is the number of people in our experimental groups. You can see the number of people in the control groups. You can see the number of comparisons, and you can see the number of studies here. And then we have our typical effect size statistics. So we can download these results as a CSV. We can download the results straight out of R from the intercept model, and we can download the results straight out of R for the no intercept model. I'm not going to go through these right now because we've looked at this in other tutorials on how to do meta-analysis in R, and it would just be really, really redundant for me to go through those again. But if you need help, please check out the playlist. There's a playlist on how to do 3-level meta-analysis in R, and we walk through interpreting those results. Okay, so like I said, we have some notes here. I'm not going to go through those right now. And we also have the R script to do all of this, including summarizing the participants, adding people, like adding the number of participants to the table, etc. Okay, so we know our categorical moderator is not statistically significant. Oh, I forgot to mention residual heterogeneity. I'm so sorry. We do include this in our table as well, and you can see that it is statistically significant. And to my brain, this may not be the 100% accurate statistical explanation, but in my brain this conceptually makes sense because we can see that we don't have significant influence of these different levels, and residual heterogeneity is testing, is there something else other than these moderators that explains the effects? And you can see that this is significant. So yes, there is something else in there that is significantly predicting the effect. Okay, so now let's move on to continuous moderators. And I actually, off the top of my head, do not remember if there are any continuous moderators in this data set. So let's just open this real quick and look. Okay, we do have one called CONT. This is completely fake data, by the way, on CONT, so I have no idea what the result will be, but we'll just select that from the column and we will click Run. Okay, so you can see here, we have our results in a little bit different format, right? So because we used a continuous moderator, I left the intercept in the model. And so what we can see here, first thing I always look at is my test of moderator, and we can see that it's not a statistically significant predictor. Okay, so that's really good for us to know. As before, we can download our formatted results, and we can download our results straight out of R if we want to, just like we could on the categorical moderators. The other thing that we have included in our table is our residual heterogeneity, and as we may expect, we see that there is something else in our data set that significantly predicts the outcome more so than this. So again, just some methods notes, same as before. I'm not going to go through those because I trust that you guys can read them if you go through this analysis. And last but not least, we have our R script here to replicate what we did. Okay, so now multiple meta-regression. Now this is really fun. It's something that's actually not used very much in my field, but I want to show it to you guys anyway because I think there's going to be more and more value to this as we get more and more studies in each area. So first thing we're going to do, as usual, upload our same data sheet. Now it's going to ask how many continuous variables we have. I only have one in this data set, that one that we just looked at. And then for how many categorical variables, I'm just going to say 2. You can go, like, I think I programmed this to go up to 20 for each one, just because that seemed like a really high number that I never expected anyone to realistically get to. But yeah, you can choose as many as you need to for your data set. So I'm going to go ahead and I'm going to select that. Now I'm going to choose my variables. And this is really important. I just want to highlight this really quickly. It actually matters which one you put under continuous and which ones you put under categorical. That's why I have them separated here with 1 on the left and 2 on the right. So make sure you choose the right thing, otherwise your results are going to be wrong. So continuous variable, I'm going to go ahead and I'm going to select that. Categorical, I'm going to select Control C because I know that's categorical. And I am also going to choose, let's say, I'll just go with voice type. That seems reasonable. So what we're doing here is we're looking to see if this combination of variables significantly predicts our outcome. So we have this fake continuous variable, and then we have the control condition and the voice type. And let's go ahead and hit run. And so what do we see here? So first and foremost, we can see, I'm just going to go down our list of things here. We have our variance components, just like we had before, right? With our within study, with our between study first and our within study second. We have our residual heterogeneity, which we can see is significant, and we can see our test of moderators is not significant. I'm not going to break down this huge table for you. If you are interested in multiple meta-regression, please make sure you interpret this table correctly. As I mentioned, this is not something that's used very often in my field, so I don't want to walk through the whole thing. But as you can see, similar to before, just kind of conceptually, we have our intercept, we have our continuous variable, and then these one labeled as factors are levels of our categorical variable. Again, we have our methods notes here, and this mentions the same thing. Categorical variables are treated as factors with distinct levels, blah, blah, blah. Moving on, you can see that we have our R script as well. And of course, you can download this R script and you can download this results as well. Okay, last but not least, we are at publication bias. So I do want to just mention that so 3-level meta-analysis essentially gets into the issue of dependent effect sizes, right? So as of now, I'm recording this in December of 2024. As of now, there are not many good ways to really, number one, detect outliers and influence and see what is significant there. So on step 3, we were using metrics that are typically used for a conventional meta-analysis, and we've just used the same thing because that's really all we got. I don't know of any methods that are specific for a dependent data meta-analysis like a 3-level analysis. So I want to mention that, but we're in the same situation with publication bias, and the difference with publication bias is there is actively ongoing work in this area right now, looking at how do we detect publication bias through different ways with dependent data. And so the last paper that I read on this was, I believe it might have been a 2023, it might have been a 2024, I don't remember, but they found there was inflated type 1 error rates for a lot of the traditional publication bias tests when they're using dependent data. And so we're not actually going to run something like, oh man, I can't remember the words right now. What are the words? Sorry, I haven't thought about meta-analysis in quite a while, which is part of the reason why I wanted to do this video today. Okay, so, failsafe n, that's the word I was thinking of. So we're not going to run a failsafe n test. We're not going to do a trim and fill test. We're not going to do any of those types of tests today. Instead, what we're going to do is primarily look at funnel plots. So let's go ahead and upload our data set one last time, and we're going to hit run. So as you can see here, it gives us a warning that we need to check our data prep. I already know that this is correct, so I'm just going to go ahead and hit generate forest plot. And you can see down here, we get our forest plots. So we have two different sizes. We can either print it out as a half page or as a full page. And when it comes to interpretation, we are using a special kind of forest plot here, okay? We're also going to be using special kind of publication bias plot. And these are from this 2020 paper, this Fernandez-Castilla et al. 2020 paper. So in this forest plot, for example, you can see the explanation here. The black boxes represent the average effect size for comparisons within each study. And the black lines are the study precision. The gray lines are the median precision of one effect size in each study. And the size of the box is representative of its weight in the analysis, and J represents how many comparisons that were analyzed in each study. So J is over here on the right. You can see the gray lines are much smaller typically within the black lines of the study. So I know that's really probably difficult for you to parse. At least it's very hard for me to parse if I just hear someone say it. So as I noted, it is written here on the screen. So when you run this data yourself, I would recommend just making sure you spend a few minutes to really think about what does this actually mean with my data. So the other piece that I'll mention is it does tell you the pooled effect size down here at the bottom of 0.29. All right, so let's scroll down and we'll get to our funnel plot. So again, we can download half page or full page funnel plots, and you can see here we have our standard error on the y-axis and our effect size G on the x-axis. So here we can see, I don't know, to my eye, this is relatively symmetrical. This is every single comparison within the analysis. And so one of the things that jumps out at me is over here on the right-hand side, we have this one study that's kind of like way out here. And then the other thing, I think it's just because these are all in a row, I realize that there's not anything relatively up here near towards the top. So that's at the comparison level, but now let's check out the study level, okay? So here we have our meta-analytic standard error on the y-axis and the study mean effect here on the x-axis. And so what we can see is we see, honestly, pretty good symmetry up here towards the top. I mean, yeah, it is a smidge, tiniest bit non-symmetrical, but it overall looks pretty good to me. Down here at the bottom, we do have this one that's kind of all by itself, so that's not necessarily ideal, but we do have a pretty good cluster up here, and it's kind of interesting that we have this big empty area here in the center. So as before, we have our methods notes and we have the R script. Now I do want to mention that the script for these is crazy long, and you can download the template for it on GitHub. I have a link here to do that, but I don't give you the script itself because right here in the interface, because it is exceedingly long. It is a very long script to be able to actually calculate, I'm sorry, not calculate, to be able to actually generate these plots. So that's basically it. I'm looking at my clock here. It says we went through this in about 24 minutes. So I'm pretty happy with that. All in all, we calculated effect sizes, we ran our meta-analysis, we interpreted it, we looked at the variance and we interpreted it and made sure it aligned with our overall analysis. We talked about outliers and influence and what those things are and what to do in different cases. We looked at different types of moderator analysis. We looked at categorical, continuous, and multiple meta-regression. And last but not least, we talked about publication bias and how it is different for dependent data meta-analyses as compared to a conventional meta-analysis. So with that said, I hope that this has been very helpful for you guys. If you have any questions, please feel free to leave questions down in the comments. And if this video has been helpful for you, please like and subscribe to help support the channel. Thanks, guys, and I'll see you in the next video.